All right. So we want to do the following. We want to prove, meaning use the precise definition of the limit, or delta epsilon. The limit as x approaches 0 from the right of 1 over x is infinity. So here's the idea. Here's what we want to do. We want to show that. So I'm just going to write out the words at first, and then I'm going to actually think about what I need to do mathematically. We want to show that for x really close to 0, that 1 over x is large. That's the whole idea. Now I need to be a little more specific about this. So what we're going to do, so how do I write that x is really close to 0? Oops. Someday my new pens are going to come in. That's our typical x minus the thing that's approaching being less than delta. Now, I feel like we have to be a little extra careful here because we're on the right side of 0. So normally we would say something like this. The absolute value of x minus 0 is less than delta. But that's really kind of more the thing we write for a two-sided limit, right? Because this means x could be between delta and negative delta. We don't actually want that here, right? Because if we want to be approaching 0 from the right, we don't want to be slightly negative. So we're actually going to say something more like, we just want x to be bigger than 0, less than delta. That's like what we actually want to say. So we're on the right side. And it's still going to be true. Yeah. Yeah. Okay. And then to show that 1 over x is large, what we're going to do is we're going to say, well, we want to show that 1 over x is bigger than, say, b for any b greater than 0. I don't know why we use b. B is a typical choice, but you can use whatever. So let me look at one thing here. Sorry. Oh, come on, mouse. Double check the thing before I say something stupid. Sorry, one moment. Also, if you have questions, you're welcome to ask them. Someday I need to look at though. Because I'll be honest, these delta epsilon things are like, they're the thing that are always like, how do you do this again? I don't really remember sometimes. So I'm just making sure I don't tell you something that is wrong. Let's see here. So, where are you? No, I can't find. Oh, there we go. Or not. Oh, there we go. Cool. Yes. Okay, that's what I thought. I just want to make sure. So we're going to, as we usually do when we're trying to prove these limits, we kind of start with the thing we want, right? Like when we're doing a delta epsilon proof, we usually start with the f of x minus the limit being less than epsilon, and we kind of work backwards until we get to the x minus the thing being less than delta. We're going to do the same thing here. So we want this. So I'm going to work with 1 over x. So if I want 1 over x to be bigger than b, well, I'm just going to solve for x. So 1 is bigger than b times x, and x is going to be less than 1 over b. Okay. So now I think we can start writing up the proof. Because I can do the following. So we're going to, and this is where, right, style depends on who your teacher is, and we'll do things one way, another way. I'm going to start with the following. Yeah. So to prove the limit as x approaches 0 from the right of 1 over x, let b be some number greater than 0. Then we're going to choose x to be less than 1 over b. Right? I know it seems kind of like, aren't you just doing whatever you want? Yeah, kind of. But that's a lot of times how these delta Epsilon proofs work. You just like, what do I need to happen? I need that. And I guess technically I should be choosing x to be greater than 0. Because, and why do I get to say that? Because we are taking the limit as x approaches 0 from the right. So it makes sense that x has to be greater than 0. It's not just because I want it to be, it's because we need it to be because of what the limit is. Well, then if that's true, that implies exactly what we want. That implies that 1 over x is larger than b. I mean, I'm really just taking this inequality and taking the reciprocal of both sides and changing the direction. Yeah. Oh, you would like to see what I'm saying? Yes, of course. Anytime. But that shows what we want. Because if you're trying to say the limit is infinity, you're saying, well, 1 over x can be however big you want it to be. And b is any positive number. So b could be a billion. And we've said, well, if b is a billion, then make x less than 1 over a billion, still positive, and then 1 over x is going to be larger than a billion. That's it. This proves it. This proves, sorry, I forgot the infinity there. This proves the limit as x goes to 0 from the right of 1 over x is as large as we want, which is what you're saying when a limit's infinity. You're not actually saying it equals the number infinity. There is no such thing. We're just saying this proves that the 1 over x function could be as large as you want it to be. How large? Be large. Yeah, these delta epsilon, the ones where the delta epsilon ones where like it equals infinity or equals negative, always seem a little bit stranger than the other ones. So that's how I would approach it. Okay, so I'm looking at you guys' various homeworks. It looks like most people are in the place of taking derivatives. Product rule. Yeses and no. I see some yeses, some no's. Okay. I would also assume then the quotient rule. Okay. We'll probably talk about this today because I imagine if you're not there yet, you're getting close to being there anyway. And I would, same thing goes for the people. If you want to tell me where you guys are at derivative wise in the chat, you certainly can. So let's talk about the power rule. So I don't think we said this in this class yet. Well, let's do the following. I'm going to use a limit definition of the derivative to find the following. Let's see, f prime of x for, let's start with f of x equal to x to the 4th. Now, I'm betting most of you know what the answer is here. Probably everyone knows. It's great. We're going to talk about the rules. Everybody probably knows or has a good idea that this derivative is going to be 4x cubed. Well, let's talk about how we show that, because this is going to lead us to the power rule. So we're going to use the limit definition. F prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. And that's going to be the limit as h goes to 0 of x plus h to the 4th minus x to the 4th all over h. Now, x plus h to the 4th is kind of a pain. And we're going to multiply it out, but we're going to do it in a smart way. So there's this shortcut trick, I don't know what you want to call it, for finding the coefficients of x plus h to some power. And it involves something called Pascal's triangle. Pascal's triangle is pretty neat. There are all sorts of cool patterns in it. And if you start writing it, you start with a 1, and then 2 more 1s. And then each subsequent row starts with a 1, and then all the middle terms are these 2 terms diagonally above it added together. So 1 plus 1 is 2. And then in the next row, you're going to have 1, 3, 3, 1. And then the next row, 1, 4, 6, 4, and so on. And it goes on and on and on and on and on. And the thing about this is each row gives you the coefficient of x plus h to that row's power. Well, if you call this top row the 0th row. So x plus h to the 0 is 1. And that corresponds to that. X plus h to the first is x plus h, or 1x plus 1h, and it corresponds to that. X plus h squared is 1x squared plus 2xh plus 1h squared. Oh, neat. And it is true that x plus h cubed, I think I have enough room here. X plus h cubed is definitely 1x cubed plus 3x squared h plus 3xh squared plus 1h cubed. The coefficients are 1, 3, 3, 1. So the way this pattern works every time is that for x plus h to any power, you start with x to that power, and then each subsequent term, the coefficients come from the corresponding row in Pascal's triangle, and the powers of x decrease by 1 every term, and the powers of h increase by 1 every term. Or the way I like to think of it is the powers always add up to the total power you're starting with. So when I'm going to write out x plus h to the 4th, I know I'm going to start with x to the 4th. And the next term is going to be 4 times x to the 3rd times h to the 1st. And then the next term is going to be 6 times x squared times h squared. And the next term is going to be 4 times x times h cubed. And then the next term is going to be h to the 4th. Minus that x to the 4th. All divided by h. Works every time. Okay, so now the non-h terms cancel, which is always what we're hoping to see when we're using a limit definition of a derivative. Right, we want the things that don't have an h in the numerator to cancel, so that everything left in the numerator has an h, which we can factor out and cancel with the h in the bottom. So we're going to factor out an h, or you can just divide each thing by h. I like to factor it out. This is the limit as h goes to 0 of h times 4x cubed plus 6x squared h plus 4xh squared plus h cubed all over h. H divided by h cancels out, leaves a 1 behind. And then we've got the limit as h goes to 0 of 4x cubed plus 6x squared h plus 4xh squared plus h cubed. And each of these things that has an h in it is going to go to 0. Because h is going to 0. So we're left with 4x cubed. So the derivative of x to the 4th is 4x cubed. And this would work for any power. So if we did it for, I don't really want to do it, but we could do it for the next one, right? If f of x was x to the 5th, our f prime of x is going to be the limit as h goes to 0 of x plus h to the 5th minus x to the 5th all over h. And we can see that what's going to happen is the same sort of thing. We're going to multiply at the top. It's going to be gross. We're going to get x to the 5th plus 5x to the 4th h plus 10x cubed h squared plus 10x squared h cubed plus 5x h to the 4th plus h to the 5th minus x to the 5th all over h. And the same sort of thing is going to happen. The non-h terms are going to cancel. X to the 5th and negative x to the 5th. Everything left has an h. And importantly, the first term that's left has h to the 1st, and every other term that's left has h to a higher power. So when I factor out an h from all of these, the first term no longer has an h in it, and every other term still does. I'm going to get a 5x to the fourth plus some other garbage that has h's in it, right? I have a 10x cubed h squared, sorry, h, not h squared, I factored out an h. I have a 10x squared h squared, I have a 5x h cubed, and an h to the fourth. And then I'm just going to cut to the chase here. Those cancel, and then the rest of the terms, as h goes to 0, are going to go to 0. And we're left with 5x to the fourth. So it seems like, I know we didn't do the first couple ones because I feel like you've probably seen them already. And it seems like when we take the derivative of x to a power, we're getting that power times x to the one less power. It happened there. It definitely happened here. And it's a pretty good guess that for f of x equal to x to some power, that the derivative is probably going to be that power times x to the power minus 1. Let's show it. We're going to actually show it. Well, we're going to show it for, oh, we'll talk about that. So let's find the derivative. So it's going to be the limit as h goes to 0 of x plus h to the p minus x to the p all over h. Is this going to be a necessary proof on exams and homework? No, you definitely, I mean, I don't imagine, depending on your class, that you need to be able to prove. Oh, and so. It's all right, you're welcome to join on Zoom. Or if it somehow, if it becomes approved, you're welcome to come back. Sorry, so someone was asking, is this going to be a necessary proof on exams and homework? And my answer is, I don't imagine so. It's definitely something you want to have seen because you want to believe that the power rule is true and not just like use it like someone told me it was true, but I don't actually know. So I'm trying to help you believe that things are actually true are true. But no, I don't think you would ever have to prove this on an exam. Not that you couldn't. I think this proof is in the realm of reasonable to be able to prove. So when we multiply x plus h to the p, well, let's see. If I look back at Pascal's triangle for a second, I know that x plus h to the 0 was that, x plus h to the first was that. I don't know what the pth row is though. Not exactly anyway. But let me ask you all a question. When I start looking at the rows, and I'm going to say this is the 0th row, this is the first row, this is the second row, this is the third row, this is the fourth row, this is the fifth row, etc. In each row, we always start with a one. Sorry, if we're going from left to right, in each row, we always start with what? 1 every time. And then in each row, the second term is always what? Yeah, whatever your power is, or whatever your row number is. So we know that if we're doing x plus h to the pth power, the second term in the row is going to be p. Just like in the fifth row, the second term is 5. And in the fourth row, the second term is 4. And because if you're going down to, you're always just adding one more, right? To get the next term here, 1 and 5 give me 6. I don't really care what's over here. And in the next row, 1 and 6 give me 7. And another term. So in each row number, the second term always has the power as the coefficient. Meaning, I don't know exactly what x plus h to the pth power is, but I do know the first couple terms. I know I'm definitely going to get an x to the p. And then the next term should be p times x to the 1 less power times h to the first. Definitely, for sure, 100%. And then there's some other terms. I don't really care what the coefficient is here. I know the power is going to be x to the p minus 2 times h squared, and so on. Right, there's going to be lesser powers of x, higher powers of h, up until the very last term, which is h to the p power. Minus x to the p all over h. We're going to do the same thing we've done before. We're going to cancel the x to the p's. What remains, we're going to factor out an h. So from this first term, I'm going to factor out an h. I'm left with p times x to the p minus 1. From this next term, I'm going to factor out an h. I don't know what the coefficient is, but I'm left with an x to the p minus 2 times h, and so on, right? From all the terms, I would keep factoring h up until the very last term, I'd have an h to the p minus 1 over h. Those h's cancel. And then if I let all the rest of the h's go to 0, well, look what's going to happen. The limit as h goes to 0 of p times x to the p minus 1 plus we don't know times x to the p minus 2 times h plus a bunch of other terms that all have h's in them. And if h is going to 0, all these other terms are going to 0. Oh, sorry. You feel free to speak up if you can't see something. So this is going to be p times x to the p minus 1. Exactly like we thought it was going to be. And this is the power rule. So, power rule. F of x equal to x to some power. It is true that the derivative is equal to that power times x to the 1 less power. And although we only showed it was true if x is a positive integer power, sorry, if p is a positive integer power, right? Because this expansion we did is only true. Like you couldn't do this expansion for x plus h to the -7 halves. And there's no way of multiplying it out like that. But the power rule is still true for any power of x. This is true for any real number. So for example, if my function was, say, x to the 1/2, we could use the power rule and say, oh, the derivative is going to be 1/2 times x to the 1/2 minus 1, which is 1/2 times x to the -1/2. Oh, yep, thank you. I think zoom out a tiny bit. Brightness. I always read about brightening it up. Okay. Or for something like f of x equal to 1 over x to the 7th, before I take the derivative, I should point out the derivative is not 1 over 7x to the 6. We can only use the power rule if we have just x to a power and nothing else going on. So I would rewrite 1 over x to the 7th as x to the -7th, and then the derivative of that is going to be -7 times x to the -8th. So then we're going to just do some more examples. Like, what if we had something like more complicated, like x to the 11th plus 1 over x cubed minus the cube root of x to the 4th. So I'm going to rewrite this, because if we see things that could be written as powers of x, we want to write them as just powers of x, meaning x to a power, no radicals, no denominators, no nothing. And we can definitely rewrite. And I should say, if you're rewriting, you don't want to be differentiating at the same time. Like, I've definitely seen people rewrite this as 11x to the 10th plus x to the -3rd minus x to the 4/3, because they were doing the derivative of x to the 11th while simplifying the rest of it. We don't want to do two different things at once. We are either simplifying or differentiating, but not both at the same time. So, sorry, I forgot. I'm just trying to put my face up. Not that it's super important to see me, but I feel like it's weird if you're like, there's hands waving around and there's a person talking, but we can't see them. Hey, people on Zoom, now you can see me. Okay. So I'm going to rewrite this as x to the 11th plus x to the negative third minus x to the 4/3 power. And now that we've written everything as x to a power, it's straightforward to take the derivative. The derivative is going to be 11 times x to the 10th minus 3 times x to the negative 4th minus 4/3 times x to the 4/3 minus 1 is 4/3 minus 3/3, which is 1/3. And that's my derivative. Definitely want the power rule to feel like second nature. It's kind of the easiest derivative you're ever going to take, but it's something a little distressingly. I've seen a lot of students in the second quarter of calculus recently. Like I will ask them like, what's the derivative of x to the 5th? And they're kind of like, let me think of, like, it should be like clockwork. Like if someone's asking you the derivative of x to a power, the answer should be at your fingertips all the time. So definitely we want to spend some time practicing it. Few more examples. Why don't you guys try this one actually? Let's say that the function is 5x to the 7th plus 7x minus 6 times the square root of x plus 8. I would like you all to first rewrite it. And there's only really one. You could probably get it without rewriting this, but you could rewrite it as 5x to the 7th plus 7x minus 6x to the 1/2 plus 8. And then I would like all of you to find the derivative. I know it's a bit of typing, but if you're on Zoom and you want to type me an answer, I would love to see it. Just walk around and look at what you're doing. I know it feels so alien these days. But... I did throw something extra there that I didn't even mention, but you guys can handle it. I suppose maybe I should address it. So I asked the question without even thinking about the fact that I asked something a little extra. We've got these coefficients out here that we didn't have before, but they're not really, we almost don't even, I mean, obviously I don't even really see them. I'm just kind of like, oh yeah, 5x to the 7th. What's the derivative of x to the 7th? Right. So the derivative here is going to be 5 times 7x to the 6th. Really, we don't even usually think about this step. We just say, oh, the 7 comes down, multiplies the 5, and you get 35, x to the 6th. And the idea here, the derivative of 7, x to the 1st is just going to be 7. And you can either, you can use the power rule there. You can say, I have an x to the 1st. The 1 comes down and multiplies the 7, and the new power is x to the 0. But really, the way I would encourage all of you to think about this is this little piece here, if it was on its own, would be a straight line with what slope? 7. The derivative is 7. Right? The slope of y equals 7x is definitely 7. So if the slope is 7, the derivative is 7. These other functions have a slope that varies, but a straight line always has the same slope. So really, when you see something times a constant times just x, you're like, oh yeah, the derivative, that's just the constant because it's just a line with that slope. And then minus 6x to the 1/2, we're going to get minus 6 times 1/2 x to the negative 1/2. And then what's the derivative of 8? Big old 0. Again, you can either think of the fact that the derivative of a constant by itself is 0, or you can think of the fact that a constant is a horizontal line whose slope is 0. And then we would simplify this. This is going to be 35x to the 6th plus 7 minus 3x to the negative 1/2. And if you prefer, you might just, sometimes it's convenient to write this as 3 divided by the square root of x instead of as times x to the negative 1/2. The reason you might choose to write it this way as opposed to this way is writing it this way makes it a little more obvious what our domain might be or not include really. So that's why people like to write it like that sometimes. Yeah. So I do want to make a point, and it's something we don't really think about all that often. When you have a constant multiple of a function, it just kind of sticks around. So when you have like 5 times a function and you take the derivative, you just get 5 times the derivative. Whereas if you have a constant on its own, its derivative is 0. So for example, if we were looking at the function 6 over x to the 7th plus 1 over 2x cubed minus 5x plus 9, well, if I was going to take the derivative of that, I would definitely rewrite it first. I write it as 6 times x to the negative 7th. And be careful with this 1 over 2x cubed. You can bring the 2 up if you want to. You shouldn't. But if you brought the 2 up, it would be 2 to the negative first, which is just 1/2, which is why I'm going to leave it in the denominator. I'm going to write it as 1 over 2 times x to the negative 3rd. But just be careful there, because I've seen people, I see people bring it all up to the numerator and write it as like 2 times x to the negative 3rd. So constants usually kind of have to stay where they're at. I mean, you can move it, but it would be weird to move it. Minus 5x plus 9. My derivative is going to be negative 7 times 6 is negative 42, x to the negative 8th. Negative 3 times 1/2 is negative 3/2. X to the negative 3 minus 1 is negative 4. Minus 5 plus 0. You don't need to write the plus 0, but it's good to kind of remind ourselves that the derivative of just a constant is just 0. Let's do a couple more. We can make it a little more complicated. So we have something like this. So our function was x to the 4th times x cubed plus 1 squared. And if we have the change rule and or the product rule, we could totally use those, but we're pretending like we don't, or we actually don't. So what are we going to do? Well, we're going to multiply it out. Sometimes the best thing to do when you're trying to take a derivative is to simplify things before you take the derivative. So I'm going to rewrite this as x to the 4th times x cubed plus 1 squared is x to the 6th plus 2x cubed plus 1. I'm just multiplying out x cubed plus 1 times x cubed plus 1. And I'm going to distribute the x to the 4th and get x to the 10th plus 2x to the 7th plus x to the 4th. So now I'm going to take the derivative. You get 10x to the 9th plus 7 times 2 is 14x to the 6th plus 4x cubed. Or we might have something like this. Yes, thank you. Let's say we had f of x equal to 6x to the 5th plus 4x plus 7, all divided by 2x squared. Whenever you have a fraction and you've got just one term in the denominator, it's really not terrible to just divide everything by that one term. So I'm going to rewrite this as 6x to the 5th over 2x squared plus 4x over 2x squared plus 7 over 2x squared. We're going to have a big exodus there, but it's just one person. And then we're going to simplify. This is 3 times x cubed. 4 divided by 2 is 2. X divided by x squared is x to the minus 1st. And then 7 over 2x squared, I would rewrite as 7/2 times x to the negative 2nd. So now we can take the derivative, right? Don't forget to take the derivative. You did all the simplifying. We still need to differentiate the thing. So my derivative is going to be 9x squared minus 2x to the negative 2nd. And then the minus 2 times 7/2 is going to give me a minus 7 times x to the minus 3rd. Questions? Interesting. Oh, my hand's very red. This pen doesn't look like it's leaking though. So, is it blood? I don't think it's blood. Like, I don't think so. No, like, well, not gonna worry about it. I'll deal with it at the break. Yeah, that's sensible. And like leaky pens. Oh, okay. So, a couple other things. I would like. So I kind of want to do some. I want to move to the product rule because that's definitely what we're going to do next. And although there are some examples we can do with product rule, really the product rule makes sense to use when you have kind of other functions other than just powers of x. That's the only time. But I'd like a couple other derivatives. So there's maybe 2 or 3 derivatives we're going to talk about. We're not going to be super duper formal about them. Well, maybe. Let's talk about the derivative of 3 functions. We'll do f of x equal to e to the x. We'll also look at g of x equal to sine of x. We'll look at h of x equal to cosine of x. These are 3 functions whose derivatives are nice and not super terrible to find. So let's start with e to the x. So for f of x equal to e to the x, when we don't know what the derivative of something is, we go back to the limit definition. So we're going to say the derivative here is the limit, h goes to 0, of e to the x plus h minus e to the x all over h. And there's a couple ways of doing this. The way I'm going to do it is going to be not very rigorous. The limit as h goes to 0. I'm going to factor out an e to the x from the top because e to the x plus h is just e to the x times e to the h. Factor out an e to the x. And we're left with e to the x times e to the h minus 1. And then we're going to break it up. I mean, we're not, it's already kind of broken up. Its limit as h goes to 0 of e to the x times e to the h minus 1 over h. And the very kind of not rigorous way of showing that this limit is what it is by actually exploring e to the h minus 1 over h for a second. So let's do that. So let's do e. Just one sec, I'll move this over so you can see it in one moment. Well, I got, well, I don't want that. Sorry. Okay, there we go. So let me show you guys this. So here is the graph of e to the h minus 1 over h. And as you look, as h approaches 0, the y values seem to be approaching what? It's like 1. If you actually plug in 0, it's undefined. Whoops, too close. I don't know if I can actually get there because it's too far away. There we go, undefined there, right? But like clearly the y values are closer and closer to 1. There are other ways of kind of justifying that this limit is 1. One of the ways is by observing that, no, let's not even go there. We're just going to say that. That limit is 1. We could definitely talk about it later if we want to. That's not really the point right now. Let's look at sine. So we're going to find the derivative. We're going to look at the limit as h goes to 0 of sine of x plus h minus sine of x all over h. Now, yeah. How are we going to deal with that? Well, here's what I really want to show you actually. let's take a break. Not an actual break, a break from this problem. I'm going to graph sine. Here's good old g of x equal to sine of x. Sine has a period of 2 pi, has a range from -1 to 1, starts at 0, and then we break it up into 4 equal quarters. And it goes up to 1 at pi over 2, back to 0 at pi, down to -1 at 3 pi over 2, and back to 2 pi, back to 0 at 2 pi. And it looks like this. I mean, you know, sometimes it looks better than this. But there's what it vaguely looks like. You can almost see it down there in the corner. And now what I really want to do is I want to graph its derivative. I don't want to give away the answer. So I'm going to just move these down. So how do we graph the derivative of the function if we know the original function? Well, the derivative is the slope of the tangent line, the rate of change. So I can see that right here at that point, the tangent line is horizontal. And the same is true over here at that point. So we know that at pi over 2 and at pi, the derivative is going to be 0 for sure. Because again, the derivative is just the slope of the tangent line. Now at 0, the function here has a positive slope. And it seems like it's probably not a huge stretch to guess that that tangent line there looks like the line y equals x. And I've drawn it pretty well. And the tangent line there would be the tangent line y equals x, which has a slope of 1. And so right here, slope of the tangent line is 1. And right here, the slope of the tangent line is -1. And over here, the slope of the tangent line is once again +1. If you look at this, what trigonometric function does it look like I'm getting is the derivative? Definitely looks like cosine. It definitely is cosine. The derivative of sine of x is cosine of x. And if you did this graphical thing again to find the derivative of cosine, might as well do it. Moving the board very strangely. So if I find the derivative of this, so let's see, now the slope of the tangent line here is 0, and here is 0, and here is 0. So maybe a 0 there, and a 0 at pi, 0 at 2 pi, and then it's going to be negative here and positive there. So -1 there, +1 there. What does this look like? Well, it kind of looks like sine, but I flipped it over. That's the negative of sine. So the derivative of cosine, which is the second derivative of sine, would be negative sine of x. I think it's good to keep these graphs in mind, because if you ever forget like what the derivative of sine or cosine is, you can always be like, oh, well, I know the graph thing does this thing. So you can really easily reconstitute the derivative of sine by just looking at the graph of the derivative. But we definitely can see from these graphs, oh yeah, the derivative of sine is cosine, the derivative of cosine is negative sine. I should point out, we're going to see a pattern for the derivative of all the trig functions in a little while. And we're going to notice that for every co-function, cosine, cotangent, cosecant, all of those derivatives have a negative derivative, whereas the other trig functions, sine, secant, and tangent, all have positive derivatives. It's a nice pattern to be aware of. It's like, oh, it's a co-function, its derivative is negative. Back to this, though. Do we need to deal with this? It's probably worth looking at. Your teachers are probably going to show it to you. So let's look at this really quick because it's maybe worthwhile. So we're going to rewrite sine of x plus h. You're going to use the angle sum formula. And sine of x plus h is, I need the limit. it's sine of x times cosine of h plus cosine of x times sine of h minus sine of x all over h. Which seems not particularly helpful, maybe. So here's what we're going to group some things together. We're going to rewrite this as the limit as h goes to 0. And I'm going to put the sine of x terms together. So I'm going to have a sine of x times cosine of h minus a sine of x all over h. And then I also have a plus cosine of x times sine of h all over h. Please stop me if you have questions. Okay, so now here's what we're going to do. For this first fraction, we're going to factor out the sign. So we rewrite this as the limit as h goes to 0 of sine of x times cosine of h minus 1 all over h. And for the second one, I'm going to factor out the cosine. Cosine of x times sine of h over h. All right, let me ask all of you a question. What's the limit as h goes to 0 of sine of h over h? Did we spend time talking about this? It's not infinity. It's not a bad guess though. It is 1. Right? I think we did the sine, so it could have. I'm always like it could have been the other A class I'm teaching. I'm pretty sure we talked about how if you have sine of stuff over the same stuff and the stuff's going to 0, the limit's 1. Slightly harder question to answer. The limit as h goes to 0 of cosine of h minus 1 all over h. This one is not quite as common, but it still comes up. So let's just do it real quick. I'm going to multiply the top by its conjugate. So I'm going to the limit as h goes to 0 of cosine of h minus 1 over h times cosine of h plus 1 over cosine of h plus 1. We multiply conjugates together, the middle terms cancel. So we end up getting cosine squared of h plus cosine minus cosine, and then minus 1. Cosine squared h minus 1. I really wish that was the other way around. Because we know that 1 minus cosine squared is equal to what other trig function? Sine squared. So let's factor out a minus. Let's say that this is -1 times 1 minus cosine squared of h all over h times cosine of h plus 1. And now that's going to be sine squared. -1 times sine squared of h over h times cosine of h plus 1. And then we're going to break this up in a convenient way. I see a sine of h over h. That's not all I see, but it's an important piece I see. So I'm going to say sine of h over h. And then what's left? Well, if I have one sine of h on top, I still have another sine of h. And in the denominator, I still have this cosine of h plus 1. Okay, I'm going to ask the same question I asked before. What's the limit as h goes to 0 sine h over h? Still 1. And if h is going to 0, what's sine of h over cosine of h plus 1 going to be? Well, sine is going to 0. And what's cosine of 0? So I get 1 plus 1, which is 2 on the bottom. As long as we're not dividing by 0, we're safe. This is going to equal -1 times 1 times 0, which is 0. Which is good. That's what we wanted. Because now look back. What's going to happen is the limit of this part is going to be 0. And the limit of this part is going to be 1. Which means the overall answer here is that we get sine of x times 0 plus cosine of x times 1, which is just cosine of x, which is the derivative, right? Remember, I know it's been a while. Remember where we started? We started with, we were taking the derivative of sine of x. So you've actually shown the derivative of sine of x is cosine x. And again, to kind of, oh, how they, one sec. So to answer the question that no one's asked, I don't imagine you would ever actually have to show this, but it is something people usually expect you to have seen. How did I get sine squared of h? I multiply cosine h minus 1 times cosine h plus 1 to get cosine squared h minus 1. And then I factored out a negative 1. So this is really equal to negative 1 times negative cosine squared of h plus 1, which I then wrote as negative 1 times 1 minus cosine squared of h. And 1 minus cosine squared of h is equal to sine squared of h. And we have this tree identity that sine squared of h plus cosine squared of h equals 1. So I'm using that identity. I'm just saying, oh yeah, cosine squared is 1 minus sine squared. Replacing that with that. Welcome. So now we've got those derivatives. Derivative e to the x is e to the x. The derivative sine of x is cosine of x. And we're not going to do the same work, but you could do similar work that we just did for this derivative to show that the derivative of cosine of x is negative sine of x. But I don't think we need to. So now we have a few rules in our playbook, I guess, in our catalog. We know that, so I'm going to introduce an notation that I prefer. So you can either write something like f of x is x to the p, and f prime of x is p times x to the p minus 1. But an alternative way of writing this is the derivative d dx of x to the p equals p times x to the p minus 1. Means the same thing, just different notation. This is called the Leibniz notation. I'm writing the derivative of my function with respect to x is equal to that. And you'll see both for sure. So we've got this rule. We know that if our function is e to the x, the derivative is also e to the x. Or using the Leibniz notation, the derivative of e to the x equals e to the x. We also have f of x is sine of x. The derivative is cosine of x. If f of x is cosine of x, the derivative is negative sine of x. We're using the Leibniz notation. Derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. Great. There's definitely more rules we're going to learn, but you should definitely memorize these. They're going to come up all the time. You won't be able to help yourself from memorizing these. They just come up so frequently. I will also just mention, this is the only type of function that's its own derivative. So whenever someone says, what's a function that's its own derivative, and people do ask that kind of question, they're like, oh yeah, there's a function, it's its own derivative. What is it? It's e to the x. Now there's a couple variations on this. It could be e to the x. It could also be 5 times e to the x. Because a constant times e to the x is still, its derivative is still the same thing. And the only other function that's, I guess, minorly different is 0. The derivative is 0. But you can really just say it's 0 times e to the x. So any function that's its own derivative is some constant times e to the x. There's no other candidate for a function with its own derivative. Here we come back around. So why are we spending all this time talking about this? Well, because I want to be able to ask questions like, what's the derivative of x to the 4th times sine of x? Oh yeah, thank you. So I want to know what the derivative of that is. And currently, we don't have the tools to do that. We need what's called the product rule. And we're actually going to derive it because it's not terrible. I have enough room here? Not really. So let's just write some words. We need the product rule. Well, let's do it. So let's say, so usually people do this in the following way. Let's call capital H of X equal to the product of little f of X times G of X. Most books usually use a capital F instead of a capital H, but I find it nicer to have a different letter so we're not confusing our F's with our F's. We want to find the derivative. Well, I want to make it really extra super clear. The derivative is not f prime times g prime. So just so everybody knows, the derivative of h of x here is not equal to f prime of x times g prime of x. In fact, a really good example of this is, let's say your function, this is going to be kind of silly, but very informative. Let's say your function h of x was x squared times x cubed. Now we know we can simplify that. What's x squared times x cubed equal to? I think that's all right. My hearing is not always the best, I've noticed, but that's all right. And what's the derivative of that? Right, thanks. But I want to make it clear to everybody that you could not take the derivative of this doing the product of the derivatives, right? It's not true that h prime of x is not 2x times 3x squared, right? That gives us the wrong answer. That's going to be 6x to the third, which is definitely not the derivative of x to the fifth. So I want to make it extra super clear that when you take the derivative of a product, you can't just differentiate each piece and multiply together. And the reason I'm emphasizing this so much is because I see so many people do it so many times. So just be careful. We'll show you the right way to do this. So we're going to use the limit definition. Limit as h goes to 0 of h of x plus h minus h of x all over h. And that's always kind of where we go back to. If we don't know how to differentiate something, go back to the limit definition. Okay. Gurgling in my water there tells me it's about time to take a break. We'll finish this first and then we'll take a break. So let's rewrite this. I'm going to rewrite h of x plus h as, well, h is really f of x times g of x. So h of a thing is h of, sorry, I'm getting rid of the h, apologies. It's f of x plus h times g of x plus h minus f of x times g of x all of h. Okay. Good so far? Right. Now all we're going to do is we're going to add and subtract something that makes everything work out the way we want it to. So I'm going to rewrite this as the limit as h goes to 0 of f of x plus h times g of x plus h minus a thing plus a thing, and then minus f of x times g of x. So I'm just going to add and subtract the same thing. I'm going to add and subtract the following: f of x times g of x plus h and f of x times g of x plus h. But now we're going to break things up into convenient pieces. Specifically, these first two pieces over h and these second two pieces over h. So I'm going to rewrite this as the limit as h goes to 0 of f of x plus h times g of x plus h minus f of x times g of x plus h all over h plus f of x times g of x plus h minus f of x times g of x all over h. So from this first fraction, what can we factor out from the numerator? What's the only thing that's appearing twice in the numerator? It's the d of x plus h. So I'm going to rewrite this as the limit as h goes to 0 of, I factor out the g of x plus h, I'm left with an f of x plus h minus f of x all over h times a g of x plus h. Then we do the same thing over here for this piece. I'm going to factor out the f of x that's common to both parts and be left with a g of x plus h minus g of x all over h. Now we're getting to the fun part. As h goes to 0, what's the limit as h goes to 0 of f of x plus h minus f of x all over h? Thank you so much. This should look like something we're very familiar with. It's the definition of the derivative of f. So this whole thing here is f prime of x as h goes to 0. And this part here is going to be g of x because h is going to go to 0. And f of x doesn't have anything to do with h, right? It's just f of x. There's no h's there to contend with. But then this part here is also going to be the derivative of g as h goes to 0. So we end up with f prime of x times g of x plus f of x times g prime of x. And that is the derivative of f times g. So there is your product rule. The derivative of f of x times g of x is equal to the derivative of f of x times the not derivative of g of x plus the not derivative of f of x times the derivative of g of x. Or as I often say when I'm thinking of it, the derivative of the first thing times the second thing plus the first thing times the derivative of the second thing. You always get the derivative of one piece times the not derivative of the other piece. And then you add them all together. Or written in the other notation, the derivative of f times g equals f prime g plus f g prime. Sometimes we omit the x's just because we all know that we're talking about a function of x and we're lazy. So we're just like, oh yeah, there's the derivative. So here is your product rule. And I want to show you that it works. So let's look back at the function I was talking about earlier, x squared times x cubed, which is really just x to the 5th. And before we saw, well, it's definitely not true, right? The derivative is not 2x times 3x squared, which would be 6x to the 3rd. We know that's not the derivative of x to the 5th. We know it should be 5x to the 4th. But now let's actually use the product rule on x squared times x cubed and see that the answer is correct. So we use the product rule there. It's going to be the derivative. So if I call if I'm calling this f and this g, it's going to be 2x times x cubed. That's my f prime, my g. Not that you need to label these things when you do it, but I'm just trying to show you. And then I'm going to get x squared times 3x squared. My f times g prime. And then simplifying, 2x times x cubed is 2x to the 4th. X squared times 3x squared is 3x to the 4th. And we end up with 5x to the 4th. As expected, the derivative of x to the 5th should be. So there's some evidence that the product rule really does do what it's supposed to do. Now, you would never use the product rule for this because you would just simplify it and say it's x to the 5th and take the derivative the normal way. But we can now answer the question that we started all this thing with was, what's the derivative of x to the 4th times sine of x? So if your function is x to the 4th times sine of x, the derivative is going to be 4x cubed times sine of x. Yes. Plus x to the 4th times the derivative of sine of x, which is cosine of x. And if you find it helpful, I do encourage you to be like, okay, that's going to be, I wouldn't call it f because I've already used f as the name of the function. So typical choices for names of the pieces are actually U and V are pretty standard choices. Just kind of terrible because U's and V's often look the same. But you would say, okay, that's my U prime times my V plus my U times my V prime. Again, not at all necessary to write that, but it helps you keep track of things. It is a good idea to write. All right, let's take a quick little break so I can grab some water and wash off the pen or blood from my hand. And I'll be back shortly. You're welcome to use the restroom. You're welcome to do whatever. I'll be back in like a couple minutes. You're always welcome to use the restroom. Right. Continue on. Sorry. All right. Excuse me. So let's look at some more examples. I'm not sure if that was blood or pen, but let's say our function is y equal to x to the fourth plus 2x times x squared plus 3. And I am going to start using the notation that I feel like most people are going to use. You could certainly say find y prime, but I would rather say find dy dx, which is just notation for the derivative. When you see this dy dx, you do read it as dy dx. You know, people don't typically say over. So like we're not going to say dy over dx, we just say dy dx. But what you should think about when you see this is it's the change in y with respect to the change in x. It's how y is changing as x is changing. It's a rate of change. And we're going to do it two ways. We're going to first simplify, and then we're going to use the product rule. So one way would be to first rewrite y as, let's just multiply it out. I'm going to get x to the fourth times x squared, so x to the sixth plus 3x to the fourth plus 2x to the fourth. Sorry, 2x cubed, apologies, not 2x to the fourth, plus 6x. So simplifying, or sorry, differentiating, we're going to get 6x to the fifth plus 12x cubed plus 6x squared plus 6. Sure. Alternatively, we could think of this as an f times a g or a u times a v, whatever letters you want to use, and say that the derivative dy dx is going to be f prime, so 4x cubed plus 2 times g, which is x squared plus 3, plus f, which is x to the fourth plus 2x, times g prime, which is x squared. Now, certainly, I think the first way of writing it seems a lot more simplified than the second way of writing it. We could simplify this. I don't really think, no, we should, just to see that they're actually the same. So we multiply this out. 4x cubed times x squared is 4x to the fifth. 4x cubed times 3 is 12x cubed. 2 times x squared. 2 times 3. X to the fourth times x squared. I'm a little worried. No. Yeah, I'm a little worried. I feel like I made a mistake somewhere. I did make a mistake. So here's what would happen if I kept going. I get an x to the sixth. And I don't have an x to the sixth in my derivative. What did I do wrong? See, I'm supposed to have, is my f prime right? Yeah, f prime is good. Is my g right? Yeah, g is good. My f's right. Is my g prime right? No, it's not. It should have been 2x. So 2x times x to the fourth is 2x to the fifth, and 2x times 2x is 4x squared. If we simplify this, it should turn out to be the same. 4x to the fifth plus 2x to the fifth is going to be 6x to the fifth. 12x cubed is the only x to the third term. 2x squared plus 4x squared is 6x squared plus 6. And yeah, they're the same. But in my opinion, it's easier to just multiply this out first. If you're trying to get a simplified answer that's all like not stuff multiplied together, I think it was way easier to multiply it out first and then take the derivative. And that's usually a good piece of advice. If you can simplify something before differentiating, it is often a good idea to do so. For example, no, we're not there yet. Not for example. Let's say we want to differentiate x cubed times e to the x. Well, here we're forced to just use the product rule. Right? There's no simplifying this into pieces that are just going to differentiate. You have to use the product rule. So the product, or the derivative of the product, is going to be, well, the derivative of the first piece times the second piece plus the first piece times the derivative of the second piece, which is also e to the x. So don't get confused, right? The derivative of e to the x is just e to the x, so it comes up again. I would leave this as is. Some people, but you might, for example, want to answer a question. I know that's super vague. Let me be a little more specific. Someone might ask the question, where does this function have a horizontal tangent line? Okay. That's just a code, and it's not really a code. But really, what are they actually asking for? They're asking where the derivative is what? Well, the tangent line is horizontal, the slope of the tangent line is 0. And so when someone says, where does this function have a horizontal tangent line? They're really just asking, where does this function have a derivative that's equal to 0? So we want to set the derivative equal to 0. So if I'm setting 3x squared plus 3x squared times, let's just write that again. If I'm setting 3x squared times e to the x plus x cubed times e to the x equal to 0, you can probably pretty easily see that x equal to 0 is going to be a solution. But it's not the only solution. And the way to find all the solutions, usually when you're setting something equal to 0, is by factoring. So what can I factor out from both of these pieces? Well, definitely e to the x. What else? I heard someone kind of whisper it, x squared. From this first piece, I'm left with a 3. From the second piece, I'm left with an x. So either this factor is 0, which means x would be what? Or this factor is 0, which means x would be 0. Or this factor is 0. Can you do x ever equal 0? No. So this doesn't give us anything. Can't equal 0. So we get two solutions. We have a horizontal tangent when x equals 0 and when x equals -3. And you can actually see that if we look at the graph. If I can get my mouse over there. If we graph x cubed times e to the x, you can see, oh yeah, at 0, there's clearly a horizontal tangent line that is y equals 0. There's a tangent line. Sometimes tangents do go through the graph. They're kind of special points. They're usually called inflection points. If the tangent line happens to be going through the graph, it's usually because there's an inflection point there. An inflection point is where so I know that I'm saying words like you might not have heard yet. Inflection point is where the concavity of the graph changes. So I would point out that, so the graph is opening upwards over here, it's concave up. The graph is opening downwards here, it's concave down. And this point is where the concavity is changing. Again, not super important. And then we would also see that there, I should zoom out a little bit. There's also a horizontal tangent line right there at -3. Right, if you could draw, I don't know what that number is, but if we set y equal to -1.3, whatever, not 1/3, 1.314, right? We can, it was something like that. Sure. Anyway, you get the idea, right? There's a horizontal tangent line at that point. And we got those by setting the derivative equal to 0. Let's do this. I can be smart. So that's why you might want to do some factoring. Like normally, if I was finding the derivative, I would totally leave it like this. But other people might decide to say like, well, I should just factor that and write it as e to the x times x squared times 3 plus x. And that is equally good. And maybe more useful if you're trying to find where you have a horizontal tangent line. And that's kind of it as far as the product rule, right? It's, I mean, well, so that's not quite it. We're gonna revisit it when we do a product of multiple pieces. Like, actually, we should. Yeah, that's a good point, James. You should do that. Is it weird that I talk to myself sometimes? So we should look at. I want to find the derivative of f of x equal to x to the 4th times e to the x times cosine of x. I've got a product of 3 things. So the problem with the product rule is it's really only, well, the original version is really only good for a product of 2 things. You got a function times another function, it's the derivative of the first piece and the derivative of the second piece. In fact, before we do this, let's actually look at just a very general product, derivative of a product of f times g times h. I'm going to try and do as little writing as possible here. So what I'm actually going to do for a moment is I'm just going to think of g times h as one piece. I'm going to call it v for a second. So I really want to find the derivative of the product f times v. Well, great, we know how to do that. It's just f prime v plus f times v prime. But now we're going to remind ourselves that v actually isn't just v. V is the function g times the function h. So I'm going to rewrite this as f prime times the function g times the function h plus f times the derivative of the function g times the function h. And then we're going to use the product rule again. The derivative of g times h necessitates the product rule. This is going to be f prime times g times h plus f times, now the product rule, g prime times h plus g times h prime. Or f prime times g times h plus f times g prime times h plus f times g times h prime. And there is a nice pattern. Whenever you have a product of more than two things, or really a product of any number of things, here's what typically happens. The product of, say, the derivative of the product of three things, you get three pieces. Each piece has one derivative, and the other two, and the rest of the pieces have their not derivatives. And that pattern always holds. Meaning, if I want to take the derivative of a product of four things, f times g times h times j, I know it's going to have four pieces. And each of those pieces is going to have one derivative and the rest not derivatives. And each function's derivative has to show up once. So I know it's going to be f prime times g times h times j plus f times g prime times h times j plus f times g times h prime times j plus f times g times h times j prime. For sure, 100%. You don't really need the parentheses, but it makes it easier to see what's what. So the product of many functions, you can only see the derivative of in this way. So if I was going to take the derivative of x to the fourth times e to the x times cosine of x, up here, like, okay, it's going to be the derivative of x to the fourth times the other two pieces left alone, plus the derivative of e to the x, which is e to the x, times the other two pieces left alone, plus the derivative of cosine of x, which is negative sine of x, times the other two pieces left alone. And it doesn't matter what order you multiply things in, which is why here I wrote them, like I wrote f, g, and h all in order, whereas here I put the derivative thing out in front. Doesn't matter. Order of multiplication never matters. I should take that back slightly. It's not the order of multiplication never matters. It never matters for real numbers and functions. But later on, when I imagine many of you will probably take 22A and 22B, talk about vectors and matrices. For matrix multiplication, the order does matter. So it's not always true the order doesn't matter. But in this class, when you're multiplying things, order never matters. A times B is B times A. We're always good. So that's how we would take the derivatives. And I would not bother trying to simplify this at all unless I had to do more with it. Obviously, you could factor out an x cubed and an e to the x if you're trying to set this equal to 0, but we're not going to do that. And in general, I would say if you're differentiating, oh, my nose really itches. Sorry, one sec. Okay. So I would say in general, if you're differentiating something, if you're not being asked to simplify it, you shouldn't. There are usually two good reasons to simplify a derivative. One, you're going to try and find where it's equal to 0 or equal to something, but usually 0 is what you're seeing. Or two, you're going to take the second derivative. Taking the second derivative is most of the time a good idea to simplify it. Although simplification right, is kind of a bloated term, because while I would certainly agree that you might think of this as being the simplified version of that, I would probably take the derivative, the second derivative of this using the red version here. I think it's easier to differentiate that than it is to differentiate that. So it's some matter of experience and like a matter of opinion, what you feel like is an easier thing to do. But most of the time it's easier to differentiate something if you simplify it a bit. All right, so that's kind of most of what there is as far as the product rule is concerned. Let's go ahead and also talk about the quotient rule. And then, yeah, and we'll see. So there's also a quotient rule. And the thing I like to think about when I think about the quotient rule is it's very, very similar to the product rule. So let me just point out, for the product rule, for h of x equal to f of x times g of x, I'm just writing h of x again because we're going to use that notation again. The product, sorry, I didn't say quotient rule, but here's the product rule over here. The derivative of this was f prime of x times g of x plus f of x times g prime of x. Now, a couple things. When I think about this in my head, I say it in a slightly different way than I actually write it. I usually think of it as the derivative of the first thing times the second thing plus the derivative of the second thing times the first thing. But again, order of multiplication doesn't matter. I'm just always thinking of it as a derivative of one piece times the not derivative of the other piece, and I need all the combinations that we could possibly get. But there's a nice reason to write it this way, in that if you write it this way, it looks very similar to the top piece of the quotient rule. So if I take the derivative of, let's say I've got h of x equal to f of x divided by g of x. I'm going to tell you what the answer is first, and then I'm going to tell you how we get there. Oh, I would never have done it that way, Grant. So there are lots of ways of doing this. So here's what we get. The derivative here is, and here's how I say it. It's the bottom times the derivative of the top. But I'm going to write it in the same way as the other one. So I would usually, if I was actually doing it, I would write it as g times f prime, but I'm writing it as f prime times g. Minus the top times the derivative of the bottom, all divided by the denominator squared. If you look at that, you will notice that the numerator of the quotient rule derivative and the product rule are virtually the same. The difference is there's a minus sign there, which means you have to be extra careful, because while it doesn't matter which order you add things in here, like you could totally write this as fg prime plus f prime g and you do the same. If you get the order wrong here, it does matter, right? Order of subtraction really matters. 2 minus 5 is different from 5 minus 2. Order of addition doesn't. 2 plus 5 is the same as 5 plus 2. So just a little careful. I'm going to close it. So how do we get this? Well, apparently there's multiple ways here. After this, I've never looked at it this way. It's kind of interesting. Oh, how? That's funky. So here's a slick way of doing this that I've never seen before, but I'm going to show it to you because I think it's neat. Your teacher might show you a different way of doing this. And so, yeah, let's solve this. Let's say that solve this. James, what are you saying here? I'm going to change this around and isolate f of x. I'm going to multiply both sides by g of x. So I'm going to say that f of x equals h of x times g of x. Is everyone okay with that? I mean, it's not doing anything super tricky, just like, am I okay with that? Yeah, I'm okay with that. Let's use the product rule. So f prime of x is equal to product rule. It's going to be h prime of x times g of x plus g prime of x times h of x. That might be not that might not be the normal order, right? Things out in, that's fine. And now I want to solve for this guy here. Right? Because that's what I'm trying to figure out is what's h prime of x. So let's subtract a g prime and an h. So I'm going to have, I'm going to have h prime of x times g of x equal to this f prime minus g prime times h. Okay, but let's replace h with what it's actually equal to. So h is equal to f over g. This is actually going to be h prime of x times g of x equal to f prime of x minus g prime of x times f of x over g of x. And then I'm going to divide everything by that g of x there. Okay, so now I've got h prime of x equal to f prime of x minus g prime of x times f of x over g of x all over g of x. And now check out this slick move. I'm going to multiply the top and bottom by g of x. It seems like a good idea because I want to get g of x squared in the denominator, so it feels like the right thing to do. And it is. In the denominator, we're going to get g of x quantity squared. In the numerator, we're going to get g times f prime. Great. I'm going to get f prime of x times g of x. And then if I multiply the g of x here, the g of x will cancel that g of x. And we're going to be left with f of x times g prime of x. Or g prime of x times f of x, either way you want to say it. I'll be honest with you, I've never seen it done this way before, but I think it's pretty cool. Another way of doing this, which is probably what's shown in your textbook, or will be shown by your professor if they show it, is that it's very similar to what we did for the product rule, where you add and subtract a piece that then makes it so you have like two derivative pieces showing up and it works out just fine. But this is also, I think, a nice way of doing it. All right, what time is it? Okay. A mnemonic device people use that I don't use, but other people do, is people like to say the derivative of the high over the low is low d high minus high d low over low squared. People kind of sing it sometimes. I don't sing it. I mean, not that I don't sing, but to me, that just doesn't ring nicely to me. I say the much less nice sounding thing. It's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom square. I mean, it's obviously a lot easier to say this, but that's not what my brain says. My brain really says bottom times derivative of top minus top times derivative of bottom all over the bottom squared. That's really what I'm thinking of every time I do this quotient rule. Okay, so now that we have the quotient rule, we can find derivatives of quotients that can't be simplified. For example, what if we had something like f of x equal to x to the sixth over x cubed plus 3x plus 1. So now we're going to just differentiate this with the product. I keep saying the quotient rule. So f prime of x is going to be the bottom, x cubed plus 3x plus 1 times the derivative of the top minus the top times the derivative of the bottom, which is going to be 3x squared plus 3, all divided by the denominator squared. And again, without a good reason, I'm not simplifying that. I will certainly point out this one is not terrible to simplify in that it actually comes out nice if you simplify it because you just get powers of x. But even then, I wouldn't simplify this without a good reason to. If you're doing web work, Really, if you're doing web work, the only reason to simplify something is just to make it not terrible to have to type out. Like sometimes it's just better to simplify it because you don't want to type all the things. But oftentimes I would just do something completely unsimplified for web work. On the other hand, if we were differentiating the reciprocal of this, x cubed plus 3x plus 1 over x to the 6th, while you certainly could use the quotient rule, I think it's a better idea to just simplify this first as x cubed over x to the 6th plus 3x over x to the 6th plus 1 over x to the 6th, which is then x to the negative 3rd plus 3x to the negative 5th plus x to the negative 6th. And then the derivative is going to be negative 3x to the negative 4th minus 15x to the negative 6th minus 6x to the negative 7th. To me, that feels like less work than using the quotient rule. You could also use the quotient rule, though. It wouldn't be terrible. Let's look at another example. Let's say our function was y equal to x over e to the x times x squared plus 1. I mean, something I should mention is technically, once you know the chain rule, you never, ever have to use the quotient rule. I still think you should. The teacher's going to teach it to you, but you can totally get away with not using the quotient rule if you really want to. We're not there yet, though. So if I want to find the derivative, it's going to be the bottom, so e to the x times x squared plus 1 times the derivative of the top. What's the derivative of x? 1 minus the top times the derivative of the bottom. For the derivative of the bottom, I'm going to have to use the product rule because it's e to the x times a thing. So it's going to be the derivative of e to the x times x squared plus 1, which is going to be the derivative of e to the x, which is e to the x times x squared plus 1, plus e to the x, not derivative, times the derivative of x squared plus 1, which is 2x. All divided by e to the x times x squared plus 1 quantity squared. Could you simplify this? Sure. Do I want to? No. Not unless someone has given me a reason to. The reason might be it's a test and I said simplify it. But right, normally not. Should we go? Oh, I don't think we need to go there yet. Okay. So we got like 9 minutes left. There are 2 or 4. Yeah, I might as well. You're going to get there sooner or later. Let's talk about a few very important quotient rules, like the derivative of tangent. The tangent is just a quotient, right? Tangent is sine of x over cosine of x. And now we can use the quotient rule. Right? No, I don't think I've ever actually seen someone take the derivative of tangent using the limit definition. Like I'm sure it's something you could do, but it's literally, I don't think anything I've ever seen in my entire life. So not that you couldn't do it, just that we never do it that way. We instead we're like, well, I know the derivative of sine is cosine. I know the derivative of cosine is negative sine. So let's use the quotient rule. Say, well, it's going to be the bottom times the derivative of the top, and the derivative of sine is cosine, minus the top times the derivative of the bottom, and the derivative of cosine is negative sine of x, all divided by cosine squared of x, the bottom squared. And although we could leave it like that, we shouldn't. So this is definitely one we should simplify. It's going to equal cosine times cosine is cosine squared of x. A minus sine of x times a minus sine of x is a plus sine squared of x, all divided by cosine squared of x. And what's a better name for that numerator? What's cosine squared x plus sine squared x always equal to? 1. And then instead of writing 1 over cosine squared x, we typically write this as secant squared of x. So,
Square x in the denominator.
correct. It's not the x that's squared, it's the whole function that's squared. And that's because, right, when you do the chain rule, right, it's the entire denominator squared, which is cosine entirely squared. Yeah. So the derivative tangent of x is secant squared of x. And that's definitely something you're going to want to memorize. And then let's talk about, yeah, we got enough time. Let's talk about the other three. So the derivative of cotangent of x, we're going to do the same sort of thing. We're going to write, so some people, yeah, fine, let's do it that way. So I would usually do it as cosine over sine, but you could also just do it as, well, derivative cotangent is really the derivative of 1 over tangent, right? Okay, so let's use the quotient rule. Bottom times, what's the derivative of 1? 0. So do be careful. A lot of times you'll have to do a quotient rule where your numerator is just a constant, and that first half of the derivative is just going to be a 0 because it's the bottom times the derivative of the top, which is 0, minus the top times the derivative of the bottom, which we just found out was secant squared, all divided by tangent squared of x. And so we get 0 minus secant squared on top, so we have a negative secant squared of x over tangent squared of x. Nobody ever writes it this way. I've never even written it that way before. Let's simplify. And so when I'm trying to simplify a trig thing and I don't know what else to do, I typically default back to writing things in terms of sine and cosine. So I know that secant is 1 over cosine. So I'm going to rewrite this as negative 1 over cosine squared of x over, and then I know that tangent of x is sine of x over cosine of x. I'm going to write tangent squared as sine squared of x over cosine squared of x. And then you could either immediately cancel the cosines, or if that is not super clear, you could flip and multiply by the denominator. And say it's negative 1 over cosine squared of x times cosine squared of x over sine squared of x. And then the cosines get to cancel. So the cosine squareds get to cancel. And we're left with negative 1 over sine squared of x, which I would rather write as negative cosecant squared of x. So the derivative of tangent of x is secant squared of x, and the derivative of cotangent of x is negative cosecant squared of x. The last two are actually easier. So let's do secant. Derivative secant of x. I'm going to rewrite secant how? Oops. Secant is 1 over. Oh, you'd like to be able to see the things maybe. So the derivative of 1 over cosine, again, quotient rule. Bottom times the derivative of the top minus the top times the derivative of the bottom, which is negative sine, all divided by the denominator squared. Simplifying this, I just get sine of x over cosine squared of x. Again, a way that nobody ever writes this derivative. The way we usually write it is, well, we're going to break it up as 1 over cosine of x times sine of x over cosine of x, which then we're going to write as secant of x times tangent of x. Before we do the last one, I want to point out a pattern that I have noticed over the years. We look back at tangent and cotangent. I'm going to make an emphasis on the co part of these trig functions. So a co-function, so when you have a function, a trig function and a co-function, they have some properties. But the one I want to emphasize here is that the derivative of tangent is secant squared. And if you just add the prefix of co on each of those, you almost get the next derivative. tangent becomes cotangent, and its derivative becomes, instead of secant squared, cosecant squared with a negative sign. So the derivative of tangent is secant squared, the derivative of cotangent is negative cosecant squared. And the same sort of pattern holds for the derivative of secant and the derivative of cosecant. So if the derivative of secant is secant of x times tangent of x, if I put a co in front of each of the trig functions, the derivative of cosecant of x we would expect to be cosecant of x times cotangent of x, but negative, because we know all the co-functions should have negative derivatives. And we don't know this, but I've said it, and we'll see it's true in a second. Let's actually do it. So the derivative of cosecant of x is the derivative of 1 over sine of x, which is the bottom, times the derivative of the top, minus the top, times the derivative of the bottom, all divided by the denominator squared. And that's going to be negative cosine of x over sine squared of x, which we're going to break up in a similar way. It's going to be negative 1 over sine of x times cosine of x over sine of x, which is exactly negative cosecant of x times cotangent of x. So there are your 6 trig derivatives in total. And they're very nice. I encourage you to memorize them. I know it's 11:50. I'm just going to write them out for you in the kind of, let me show you the standard way people typically write these out, because there is a pattern and the pattern is useful for future things. So give me just one more moment of your time. I'm going to write some things. The derivative of sine of x is equal to cosine of x. The derivative of cosine of x is equal to negative sine of x. The derivative of tangent of x is equal to secant squared of x. So we typically write the 3 primary trig functions on the left, and then across from them we write their reciprocal functions. So the reciprocal sign is cosecant. The derivative of cosecant of x is negative, right? Screw this up here. Negative cosecant x cotangent x. The reciprocal of cosine is secant, and the derivative of secant of x is secant of x times tangent of x. And the reciprocal of tangent is cotangent, and the derivative of cotangent of x is negative cosecant squared of x. So yeah, those are your 6 trig derivatives. I highly, highly recommend memorizing them. It will come up over and over and over again. And I do encourage you to memorize them in this way, where you have sine, cosine, tangent on the left, cosecant, secant, cotangent on the right. There's a couple things you get to see really nicely from this. One, sine divided by cosine is tangent. That's kind of a nice thing to see. And then across from each function is its reciprocal function. Later on, we're going to talk about some other related functions that have a similar pattern. And it's just kind of nice to have it set up this way already. All right, I should stop there. I should let you all go. See you all next time.